2.1, page 136. All right, we've mentioned this before, but our textbook assumes that we did not do the prerequisite chapter. That was just kind of like an independent review for students to do on their own as they needed it. And so as some of those topics come up through the course of the book, they're teaching them as if they have not taught them to you before. So we did the prerequisite chapter. Therefore, a lot of the stuff that we're going to look at today is review, but that's okay. We'll take it. So on 136, they talked to us about quadratic functions and how to graph them and that type of thing. And so they start off by telling us that a quadratic is a polynomial with a degree of 2. Okay, well then what's a polynomial? So there on the top of 136, they give us the definition of a polynomial. It says, let n be a non-negative integer. And when they're referring to n, they're referring to like the exponent up here. So like this might be x to the 4th, and then x to the 4 minus 1, x to the 3rd, and then x to the 2nd, x to the 1st, and so on. So they said let that exponent n be a non-negative integer. All right, why does it have to be non-negative? What if it were negative? What if that was like x to the negative 2? What does that mean? X to the negative 2, what does that mean? It's a fraction, right? That'd be 1 over x to the positive 2. So that's not a polynomial, that's a fraction. They also said that the exponents have to be non-negative integers. Integers, positive and negative whole numbers, right? Why does that exponent have to be a whole number? Like if it weren't a whole number, maybe it was like 1/2 or something like that. What if you have x to the 1/2? What is that? That's a square root. That's a radical. That wouldn't be a polynomial either. So that's why they put the stipulation on there that our exponent needs to be non-negative and it needs to be a whole number. Okay? So under those conditions, they also go on to tell us a little bit about the coefficients. It says that a sub n minus 1, a sub 2, a sub 1, a sub 0, and so on, those have to be real numbers. So when you see here a sub n minus 1, a sub 2, a sub 1, a sub 0, those just have to be real, meaning they can't be imaginary. Okay? So under those qualifications, we would have a polynomial. And they give us a couple of bold print terms there. They give us constant, linear, and quadratic. Now, when we looked at this in the prerequisite chapter, we did go through and we made a pretty elaborate chart in section, I think it was P4, where we went through and we gave an example and we told how many, what the degree of that polynomial was and what its particular name was and how many turns it made, and we drew a sample of what that graph would look like. That was where we talked about the leading coefficient test, that the leading coefficient would tell us whether it was going to end up or end down, and then we could determine by the number of turns that it made which way it started, and we would get a pretty good idea of what that graph would look like. So we've expanded on what we've got in our notes here. We've had a whole lot more in our notes, but just for a brief review, if you have a degree of 0, that's a constant function like y equals 5. If you have a degree of 1, that's linear, like x to the 1st, y to the 1st. And if you have a degree of 2, then that's quadratic, and that's where we want to focus our attention today. A quadratic function is going to graph as a parabola, and that parabola might open down or it might open up. When your parabola opens down, you're going to have a vertex. That vertex is the highest point on that graph. It is your maximum value on that curve. If your parabola opens up, your vertex is going to be a minimum. That is going to be the lowest value on that curve when your parabola opens up. If your leading coefficient A is positive, your parabola opens up. If your leading coefficient A is negative, then your parabola opens down. And every parabola is going to have an axis of symmetry. That's an axis that if you were to fold your piece of paper on that dotted line, your parabola would fold on top of itself. Now with these parabolas, because they're all opening up and down, our axis of symmetry is going to be a vertical line. Every vertical line has the equation x equals something. And if you'll notice, that axis of symmetry is running through the vertex. So whatever the x value of my vertex is going to be the same thing as the x value of my axis of symmetry. So all I have to do is look at the x value of my vertex and say x equals that number, and that will be the equation for my axis of symmetry. All right, then they tell me that there are two different ways that we typically write the equation for a quadratic. We typically write it in either y equals ax squared plus bx plus c form, or we write it in y equals ax minus h squared plus k form, where hk would be that vertex that we were talking about. That second form is our standard form. And in that standard form, you can look at it and see what your vertex is. You can look at it and see your leading coefficient to see if it's opening up or down. And you could also apply the idea of a vertical stretch or shrink based on that leading coefficient as well. So in example number 2, they give me f of x is equal to 2x squared plus 8x plus 7. They give me my quadratic in this first form, and they ask me to convert that into standard form. So they want me to change from this form into this form. All right, so here's how we're going to do that. Step number 1, we're going to move our constant to the other side. So let's take that constant, positive 7, and let's subtract it to the other side. Then step number 2, we're going to factor out our leading coefficient. So our leading coefficient, A, is 2, so let's factor a 2 out of this side. So if I take a 2 out of 2x squared, I would just be left with x squared. And if I take a 2 out of 8x, then I would just be left with 4x. And then I want to complete the square, because my goal is to create a perfect square over here, right? So I want to complete the square. So remember, the steps for completing the square are take the coefficient of the middle term, cut it in half, and square it. And then we add that to both sides. So let's take the coefficient of the middle term, which was 4, cut it in half, which was 2, and square it 4, and we'll add that to both sides. Now, there's one thing I have to watch out for here. When I go to add my 4 over here on the right-hand side, that 4 is inside parentheses that are being multiplied by 2. What did I really add to that side? When I add 4, it's inside parentheses that are being multiplied by 2. So what did I really add to that side? 8. So when we say what I do to one side, I do to the other side, I have to add 8 to the other side to compensate for the 4 that we added inside the parentheses being multiplied by 2. So we really added 4 times 2, 8. So we're going to add 8 to the other side as well. All right, and then let's simplify. So we were going through this process of completing the square to create a perfect square over here. So we did that. X squared plus 4x plus 4 would factor to x plus 2 times x plus 2. And then our negative 7 and positive 8 would simplify down to be positive 1. And then in this form, notice that y is by itself on the left-hand side. So let's go ahead and take that positive 1 and let's subtract it back over to the other side. So I moved it from its ax squared plus bx plus c form to its standard form. All right, what are the advantages of standard form? Well, I can look at it and automatically tell which way it opens. So looking at this positive 2, which way does this open, up or down? Up. I also can look at it and see my vertex, because remember that my vertex is hk. So when I'm in this form, I can just look at this and say, okay, x minus h has to be negative 2, and y plus k, y has to be negative 1. It might be easy for you to also look at it in this line up here and say, okay, any value subtracted from x is the horizontal shift of negative 2. Any value subtracted from y is the vertical shift of negative 1. That also is why our vertex is at negative 2, negative 1. Okay. If, however, you're looking at it in this form, be sure that you notice it is the opposite of h, but it is plus k. So we did the opposite of positive 2, negative 2, but we did not do the opposite of this negative 1, We just did the negative 1 as it was. Okay, so now I have my vertex. I know that this opens up. I also could say, okay, since there's a 2 out in front of here, I know that there's going to be a vertical stretch by a factor of 2. But that's pretty much all I know. In all of that work that I just did, that's all I got from it. I would propose to you, yes, there are times that I need to complete the square and I need to put something in standard form. But if the only purpose for doing that is to be able to get my vertex, to tell whether it opens up or down, and to see that vertical stretch, I can do that much easier. Here's what I could do. Let's go back to that same original equation. F of x is equal to 2x squared plus 8x plus 7. Looking at that equation, I can see that 2 right there. I can see that it opens up and it has a vertical stretch by a factor of 2. I know that already. That literally means the only other benefit of this form was the vertex. So here's a fast, easy way that if I'm in this form, here's a fast, easy way I can find the vertex. The x value of your vertex is going to be negative b over 2a. And anytime you know an x value, you just plug it in to find a y value, right? So let's do that. If x is negative b over 2a, we're looking at this like ax squared plus bx plus c, the exact same way that we did when we did quadratic formula, okay? So I could go through and I could say b is 8, so that'd be negative b over 2 times a is 2. So negative 8 divided by 4 is going to give me negative 2. That's my x value. And then to find y, we're just going to plug that x value in. And I get that exact same vertex, negative 2, negative 1. Only I get to do this much work instead of this much work. Okay? So again, there are times that I need to complete the square. But if all I need to know is which way this opens, I can look at it and see that the leading coefficient is positive, it opens up. And what my vertex is, I can do negative b over 2a to get the x value and plug that in to find the y value. I got the same information. All right, so whichever method that we go, if they gave me the quadratic in ax squared plus bx plus c form, I'd probably do the negative b over 2a thing. If they gave me the quadratic in standard form, I absolutely would just pull the vertex out of that and see if it opened up or down. But in either case, now that I have my vertex and which way this opens, I can come over here to my graph and plot my vertex at negative 2, negative 1. And I know it's going to open up, but it's going to be a little taller and skinnier, like twice as tall and skinny as a typical parabola. So I could just show it with a vertical stretch. And if they just say sketch the graph, that's perfect. If they want me to be a little more precise with my graphing, it doesn't say just give a sketch, like they actually want me to plot a few points. What we have found in the past is that some of the easiest points to plot are the x and the y intercepts, right? So your x-intercept is what you get by setting y equal to 0. So if I were to take that same parabola we've been working with, and I set f of x, or y, equal to 0, I could solve that, and that would tell me where this graph is crossing the x-axis. I also have that quadratic program on my calculator that I could use to do the same thing, to give me those x-intercepts. I could use the root button on my calculator to find those x-intercepts if I had the calculator at my disposal. If I didn't have my calculator, I definitely could do the quadratic by hand. You don't have to write that out, but I just wanted to remind you of how we did the quadratic by hand earlier this year. That quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. And again, we're talking about a is 2, b is 8, c is 7. The trickiest thing that we have found with the quadratic was be sure you follow order of operations. You can't do 64 minus 4 is 60 times 2. You have to combine the 4, 2, and the 7 before you do your subtracting. And then it's just an issue of simplifying. Like the square root of 8 simplifies down to 2 square roots of 2. I would be tempted to try and cancel like this 8 with this 4 or this 2 with this 4, but remember that you can't cancel things that are being added and subtracted. You can only cancel things that are being multiplied or divided. So the only thing I could do would be to take a common factor out of that numerator. So we took out a common factor of 2, and then I can cancel that 2 top and bottom. So this would be my answer in lowest terms. Kind of hard to graph negative 4 plus the square root of 2 over 2, so I'd have to get a decimal for that anyway. So once I get my two decimals of negative 1.3 and negative 2.7, then I could come up here and plot those as my precise x-intercepts. Another point that we typically like to find is a y-intercept. Okay, y-intercept is really easy to find with a parabola or with a quadratic, because if you think about it, we get the y-intercept by putting 0 in for x, right? So if you come back and you look at this guy right here, if you put 0 in for x, this piece goes to 0, this piece goes to 0, your c value right there is your y-intercept. So that's really nice because I could come up here to 7 and plot my y-intercept, and using that idea of an axis of symmetry, I could say, okay, if I'm at 7 when I'm 2 units away from that axis, then I could go 2 units away on the other side and plot a y value of 7, basically reflect that point over. So if I have a point at 0, 7, then I would also have a point at negative 4, 7. So if I just needed like 3 points, if I needed a vertex and 2 other points, that would do it. My vertex and my y-intercept and the reflected point that went along with it. Or I also could do as we had just looked at here and find the 2 x-intercepts by just solving the quadratic. Okay? So by that point, we definitely would have enough points to give a precise graph. All right, so let's look at some of the applications of the quadratic, where we might see it and what we might do with it. Up until this point, they've been giving me the equation and asking me to give some information. For the next problem, they give me some information and ask me to come up with the equation. So for example number 4, it says, find the standard form of the equation for the parabola that has a vertex of 1, 2, and passes through the point 3, negative 6. Okay? I know that my vertex is HK, so we can come down here and plug in HK. So I'm going to put 1 in for H and 2 in for K. The only other thing that I need then is my A value. How am I going to use that point 3, negative 6 they gave me to help me find my A value? Has to be some reason they gave it to me. How can I use that point 3, negative 6 to find my A value? Excuse me.
X and Y.
All right, it's an ordered pair x, y, so exactly, plug it in for x and y. So this 3 is x, so put 3 in the place of x. And this negative 6 is y, so put negative 6 in the place of f of x, or in the place of y. And then my only unknown is a, right? Awesome, so let's solve for it. So what do you want to do first? Order of operations says do what first? Parentheses. 3 minus 1 is going to give us 2. Then what? Parentheses, then what? Exponents. So we'll do 2 squared is 4. Then what? All right, so we'll subtract 2. And then what? Perfect. Divide by 4, and we'll get A is negative 2. So take that negative 2 and put it back up into the equation. And that'll give us the equation for our quadratic that has a vertex of 1, 2, and goes through the point 3, negative 6. All right, look at example 5. Example 5 says a baseball is hit 3 feet above ground at a velocity of 100 feet per second at an angle of 45 degrees with respect to level ground. The path of the baseball is given by this function, where f of x is the height of the baseball in feet and x is the distance that we are away from home plate in feet. So what is the maximum height reached by the baseball? All right, so here's the idea. We're standing at home plate, we hit the ball, and it basically follows a parabolic path, right? And if we think about it, they were kind enough to tell me what this is, but they won't always do that. So it might help me to kind of draw out a picture and think about it a little bit, that this would be the distance that the ball is away from home plate. I also could think about this over here if they had not told me, which they were kind enough to tell me, but if they had not, I could look at this and see what my y value represents. It just represents how high the ball is in the air, so it represents the height. When you're working with an application, most often with quadratics, your x value is going to represent when something happened or where something happened. Your y value is going to represent the actual maximum or minimum. The reason that's significant is in a word problem, they typically ask you for one or the other of those things. Like they might say, how far away was the ball from home plate when it reached its maximum height? Or they might say, what was the maximum height of the ball? But those two answers would be different things. So it's important that I answer the question that they ask. So the x value is typically when something happened or where it happened. The y value is typically the actual maximum or minimum value. So in this case, it says, what is the maximum height? They actually want the y value. Where is that maximum height going to occur? At a y value, yes, but where? What particular point? What's the name of it?
Vertex.
The vertex, right. So I need to find the vertex. So how can I find the vertex? Do you want to complete the square? Not looking like a whole lot of fun with those decimals, right? So what's my other option for finding the vertex? Negative b over 2a. Perfect. So let's do that. So let's do negative b over 2a. So what's my b value? 1. What's my a value? That nasty decimal thing, right? So we can do negative b over 2 times a. And we'll throw that into our calculator, and we'll get 156 and 25 hundredths. 156.25. Is that the maximum? What is that? That's my x value. Is that the maximum height of the ball? That's its distance, right? That's the distance it is away from home plate. When it's 156 feet away from home plate, that's when it reaches its maximum height, but that's not its maximum height. They asked me for the height, so I've got to do what with that? Plug it in. So let's plug that x value, 156.25, into the function to find y. And again, I'm going to throw that into my calculator. I'm not doing that by hand. But when I throw that into my calculator, I'll get 81.125. And that is my height. That's what they're looking for my answer. Now, if we're on a portion of a test or a quiz where we only have a scientific calculator, we're going to do what we just did right there. But if you had a graphing calculator, there would be another way that you could do this as well. Remember that you've got that maximum button on your calculator? You could put this into your calculator and ask it to find that maximum for you, right? So the way that we do that, just for review, because I know that we've done this before, but the way that we do that is we would put the equation in y equals. Now, if from there you ask your calculator to find the maximum, it's going to give you an error message, because if you ask it to do like a zoom standard where you're asking it to see tens all the way around, you're just not going to see very much on your graph, right? Because think about it. When you look at this graph, our x values are going from, well, this is only 156, so we're going out past like 300, 320, right? So my x values would have to go from like 0 to 320, and my y values would have to go from 0 to at least 81.125 for me to be able to see that whole graph. So I would have to reset my window manually to tell it to go from 0 to 320 and from 0 to 85 or something along those lines that you're comfortable with. Then I'd be able to see that graph. Then I could go to second trace, my calculate menu, choose option number 4, my maximum, and that's where it prompts me for the left boundary, the right boundary, and the guess, and then you can see it will give me that exact same ordered pair that we had up here. Okay, so just review of how we do that. All right, so here is our homework for tonight on pages 143 to 145.